Nuclear power for the 21st century. The commercial nuclear electric power industry is now 60 years old. It has had a checkered life. At times it has managed to frighten the public while still providing up to 20% of our electric power. The light water reactors in use today were invented in 1947. While improvements to safety and operations have been made over the years, the basic concepts have not changed. While aircraft and automotive design and manufacture, space exploration, computer technology, medical research and care, communication systems and technology have made quantum advances in design, cost, and reliability, commercial nuclear power has remained relatively unchanged since the launch of the first atomic submarine in 1954. Why has atomic power remained rooted into the past? I hope to shed light on this and other topics. Nuclear reactors have been around for a long time. Natural reactors estimated to be 1.7 billion years old are found in Gabon, West Africa. The soils of West Africa had much higher concentrations of U-235 billions of years ago. Groundwater seepage into these U-235 concentrations acted as a neuron moderator, allowing a chain reaction. Rising water temperature decreased the rate of reaction, thus keeping the reactor in balance and preventing explosions. These reactors may have operated in this fashion for thousands of years. Nuclear power fuels. Most fuels used in nuclear reactors today are solid radioactive isotopes. A fissile nuclear isotope is capable of sustaining a nuclear chain reaction. Fissile isotopes can be identified with a mathematical calculation. There are 33 identified fissile isotopes. Only 3 are in common use in nuclear power reactors. Uranium-233 is not considered common on Earth, but it is easy to manufacture. Uranium-235 is common on Earth, but it is not considered abundant. Plutonium-239 is not found on Earth and is man-made. Uranium-235 is the worldwide workhorse isotope. U-235 is used in research, medical and commercial power reactors, and is the preferred fuel for nuclear weapons. President Dwight Eisenhower opened the commercial age of nuclear power with a speech at the United Nations in December 1953. His intent was to defuse and de-escalate the rising tensions and fears of the American public and European allies of war with the Soviet Union. While the Atoms for Peace initiative did nothing to reduce the nuclear arms race of the 1950s, it did set the foundations of civilian use of nuclear energy. The first Generation 1 atomic power station began operations at Shippingport, Pennsylvania in December 1957. A unique thorium-fueled light water breeder reactor operated from 1977 to 1982 at Shippingport. It used uranium-233 as the fissile material. The reactor core was housed in a reconfigured early pressure water reactor. It operated with a power output of 60 megawatts and had an availability factor of 86%, producing over 2.1 billion kilowatt hours during its operation. More fissile fuel was present at the end of operations, proving the concept of the thorium breeder reactor. The Generation 1 Shippingport and reactors at Oak Ridge, Tennessee, Idaho National Labs, Argonne, Illinois National Labs, Hanford, Washington, in the 1950s and 60s, operated many Generation 1 reactors for research, demonstration, and test purposes. All U.S. commercial power reactors today use solid nuclear fuel and are light water cooled. These are boiling water reactors with one cooling loop and pressurized water reactors with a primary and secondary cooling loop. The reactors at Fukushima Daiichi, Japan were boiling water types. 3 Mile Island is a pressurized water reactor system. Fuel core assemblies remain in a commercial reactor for about 3 to 5 years. Some core assemblies are replaced every 18 to 24 months. Replacement factors include U-235 depletion and fuel assembly contaminants. Radioactive nuclide contaminants in the fuel, such as xenon, barium, strontium, cesium, and others, along with crud, degrade reactor performance and contaminate primary cooling water. U-235 starts out about 3.5% enrichment, with 1% remaining at the time of removal. About 30% of the U-235 fuel is wasted. There are currently 99 operating nuclear power plants in the United States, 65 pressurized water reactors, and 34 boiling water reactors, which generate about 20% of our nation's electrical power. Generation 2 reactors were used in the first large nuclear plants in the 600 to 800 megawatt range. Most plants were designed and constructed in the 1960s and early 1970s. The design lifespan of these plants was about 40 years. Many of the Generation 2 plants have upgraded cooling systems, instrumentation, operating procedures, security, operator training, and certifications. Their licenses are extended to 60 years. Most of the U.S. plants are approaching end of life. This is a boiling water reactor diagram. Boiling water reactors are of a single loop design. The steam entering the turbine is radioactive. Although not shown in this diagram, the turbine, generator, condenser, pumps, and associated piping must be housed in a shielded containment structure. The pressurized water reactor. Pressurized water reactors are a double-loop design. Steam entering the turbine is not radioactive. The pressurized water reactor design is more complicated and expensive. It is also safer to operate. Generation 2 reactors received improvements to safety, redundant core cooling, and emergency cooling system upgrades after the 3 Mile Island accident in 1979. Gravity feed passive emergency core cooling systems were engineered. Standardization of instrumentation, procedures, training, and certification was introduced into plant operations. Greater reliance is placed on computer diagnostics and analyzation of anomalies. Frequent inspections and certification allows increased life cycle to 60 or more years. Generation 3 and beyond. The CANDU 6, a Canadian design, AP1000, and other Generation 3 and 3 Plus reactors are designed to be much safer, efficient, and have lower construction and operational costs than previous Generation 2 plants. In recent years, opponents of nuclear power appear to have more concern with external threats such as terror attacks and aircraft collision with external structures rather than the nuclear infrastructure itself, which appeared to be the soft spot in the past. The CANDU 6, with 600 megawatts electrical output, and enhanced CANDU 6, 700 megawatts electric reactors are considered Generation 3 designs. They are used in several countries around the world. CANDU uses various types of fuels, such as uranium, plutonium, and mixed oxide fuels for efficiency and low cost. The emphasis on recycling waste fuel substantially reduces the threat to environmental impact. Advanced CANDU 6, 1200 megawatts electric, is in design and licensing phase. As of late 2014, the U.S. Nuclear Regulatory Commission has approved 5 new Generation 3 Plus designs and has 5 additional designs under review. 4 new Generation 3 Plus AP1000 plants are under construction in the United States, 2 each in Georgia and South Carolina. The CANDU fuel cycle. The interesting thing about the CANDU fuel cycle are all the arrows shown in this diagram. Different types of fuel are received from various sources, burned in the nuclear reactor, then reprocessed for another burn cycle. Countries recycling and reprocessing nuclear waste include Canada, France, India, Japan, Russia, and the United Kingdom. Notably absent from the list is the United States. Spent fuel handling in the United States. In the United States, newly manufactured fuel assemblies for power plant reactors are loaded into the core. Depleted fuel assemblies are removed from the core and placed in cooling pools for 10 years. After cooling, spent fuel assemblies are then transferred to dry casks for indefinite storage. The spent fuel casks never leave the plant property. President Jimmy Carter prohibited recycling nuclear fuel by executive order in 1977. The permanent disposal project proposed at Yucca Mountain, Nevada, was effectively suspended in 2010 by President Barack Obama, Congress, and the federal courts. Yucca Mountain and permanent storage of U.S. nuclear waste is determined by the political climate of short-term election cycles. Science, logic, engineering, and common sense have no standing in solving long-term nuclear problems in the United States. Why do we use U-235? U-235 is that workhorse of the nuclear industry. It is highly fissile and a great reactor fuel. U-238 and U-235 are found together. The ore from which uranium is extracted contains about 99.25% of uranium-238 and only about 0.75% of uranium-235. It is a large expense and a lengthy process to extract usable amounts of U-235 from the uranium ore. This is what the current negotiations with Iran are all about. U-235 concentrations below 20% is considered low enriched uranium. From 20 to 90% it is considered highly enriched uranium. Above 90% enrichment is considered weapons-grade uranium. Commercial U-235 fuel is generally enriched to about 3 to 4%. Generation 4 designs. New state-of-the-art designs may be engineered and constructed in the next 50 years. Generation 4 is an international initiative of 13 nations to study concepts and future reactor designs. 6 reactor designs are currently under review and evaluation. These designs represent advances in sustainability, economics, safety, reliability, and proliferation resistance. All Generation 4 designs operate at much higher temperatures, with efficiencies approaching 50%. Current Generation 2 plants are about 37% efficient at best. These designs are expected to be available for construction after 2030. While these designs are state-of-the-art, unproven concepts, the molten salt reactor is an outgrowth of the nuclear-powered aircraft research done at Oak Ridge National Labs in the early 1950s. The molten salt reactor experiment operated successfully at Oak Ridge from 1965 to 1969 and was a prototype of the thorium-powered breeder reactor now envisioned for Generation 4. Simplified diagrams of Generation 4 designs. These are the finalists from a list of 130 designs submitted for study. These Generation 4 reactor designs operate with much higher outlet temperatures in the range of 900 to 1800 degrees Fahrenheit, providing higher efficiencies. These designs provide heat for chemical and industrial processes. Applications include the manufacture of hydrogen, synthetic gasoline, seawater desalination, bulk industrial heat for mining and manufacturing applications, as well as electric power generation. Thorium was discovered in 1828 by Swedish chemist Jöns Berzelius. Thorium is element 90 on the periodic table. It is classed as an actinide, a silvery radioactive metal with a half-life of 14 billion years, 4 times more abundant than uranium on Earth. A primary source of thorium is a byproduct of mining rare earth minerals. About 1,000 tons of thorium contains enough energy to supply the United States with electricity for an entire year. Non-nuclear applications include welding, metal alloys, electronics, optics, and ceramics. At one time it was commonly used in mantles for gas lamps due to its high iridescence. Non-fissile thorium will not support a nuclear chain reaction. Through neuron capture it becomes fissile, a nuclear fuel stock. When thorium-232 is bombarded by slow neutrons, it undergoes a 4-step process to become the fissile isotope uranium-233. Uranium-233 is 98% efficient as reactor fuel, producing only 2% waste. In comparison, uranium-235, the current commercial reactor fuel, leaves 95% waste. Fluid uranium-233 can be used in molten salt and liquid fluoride thorium breeder reactor designs. China and Canada are currently constructing molten salt reactors. India is pursuing solid thorium-fueled reactor designs. Thorium-based uranium-233 fuel does not produce plutonium, a non-proliferation treaty benefit. While it is theoretically possible to build a U-233 bomb, the United States has tested such a device. It is very difficult, expensive, and dangerous to manufacture. The U.S. bomb was not considered completely successful. The molten salt reactor is fueled with uranium-233 dissolved in a liquid fluoride salt. Uranium-233 is produced in the reactor by transmutation in the thorium fuel cycle. Molten salt reactors are liquid-cooled by lithium fluoride salts, operating at atmospheric pressure and output temperatures in the range of 900 to 2500 degrees Fahrenheit. Liquid-fueled reactors are simple in design, allow for removal of fission and waste products, and can be refueled while operating. They are self-controlling, allowing for little or no operator intervention in case of trouble. They can be designed and constructed to be walk-away safe. The Generation 4 molten salt reactor design is an outgrowth of the molten salt reactor experiment and aircraft nuclear propulsion program developed and tested at Oak Ridge National Labs in Tennessee during the 1960s. The thorium-fueled molten salt reactor can be a safer and cheaper commercial power source with an inexhaustible supply of thorium fuel. The molten salt reactor and liquid fluoride thorium reactor use thorium as the base fuel. During the fission process, undesirable isotopes are created. These waste products adversely affect reactor operation and efficiency. Waste can be removed without shutdown. New fuel can be added. In liquid fuel environments, the mechanical structures of fuel assemblies are unneeded. Mechanical parts do not impede neuron paths and are not subject to failure due to mechanical shock like earthquakes. Raw thorium is dissolved in the fluoride solution and added to the reactor as required. The very high operating temperatures are suitable for high-efficiency generation operations and can be used for industrial, chemical, and mining operations. The molten salt reactor operates at atmospheric pressure. Heavy, high-pressure piping is not required. Reactors can be factory-made, reducing fabrication and production costs. Without the danger of high-pressure radioactive steam, containment and safety structures can be smaller and lightweight. Molten salt is not reactive with air or water. While radioactive, a salt spill will solidify in place, limiting its spread and making cleanup easier. Molten salt reactors are designed to be self-throttling. As temperature increases, the fission process slows down. Molten salt reactors are walk-away safe. In case of overheating or loss of electrical power, a refrigerated freeze plug will melt, releasing the nuclear fuel into a subcritical underground storage system where it cools and solidifies. Virtually no plutonium is created from burning thorium in molten salt reactors. Plutonium waste from Generation 2 light water reactors can be used as a mixed oxide fuel in molten salt reactors, burning as much as 75% of the plutonium in a single pass. Burning mixed oxide fuels frees plutonium and other isotopes from the waste stockpile and potential proliferation paths, and reduces long-term permanent waste storage requirements. The thorium fuel cycle is naturally resistant to producing nuclear weapons, but not impossible. The process for making a U-233 bomb is considerably more expensive and complicated than producing a U-235 weapon. Radiation hazards to workers are significantly higher than other weapons work. Remote manipulation tools are required. Limited testing and research has been done by the United States, and results were never considered satisfactory. A government wishing to choose the U-233 bomb path would make a substantial investment in capital, time, and resources with no assurance of a successful outcome. It is still possible. The thorium fuel cycle, a simplified description. Raw thorium alone is not fissile, therefore cannot be used as a nuclear reactor fuel. Thorium must be coaxed or jump-started into giving up its energy. An external source of neurons is required to begin the thorium fuel cycle. Thorium in solid or liquid form is loaded into a suitable reactor, and a small amount of fissionable material such as uranium-233, uranium-235, plutonium-239, or a combination thereof is added to the fuel mix. A neuron from the fissile starter fuel is captured by a thorium-232 atom and begins the four-step process of converting thorium-232 into fissile uranium-233. This process continues until a critical mass of uranium-233 is produced in the reactor. Beyond this point, only thorium need be added to maintain the chain reaction in the uranium-233 fuel. While there are a host of economic, environmental, social, and political excuses not to advance our nation's technical infrastructure, the fact of the matter is, Americans are comfortable the way things are. History has shown America's finest times are those of crisis. We shine in revolution, civil conflict, the great wars and economic disasters of the 20th century. Our transportation, power, water, communications infrastructures, healthcare and education will not receive our attention until they fail from natural or man-made abuse. The nation and the world has an ample supply of scientists, inventors, entrepreneurs, and visionaries to solve problems. America lacks the caliber of leaders such as Washington, Lincoln, Roosevelt, and Kennedy to motivate us off the couch.